We have one more thing to talk about in this unit, Mr. Demetrius, and that is what?
Polarity.
Polarity?
Yeah.
Now, polarity has to do with poles. You've got the North Pole, the South Pole on the Earth. Magnets have North Poles and South Poles, so molecules can have poles.
Yeah, it doesn't not only have to deal with north and south. Anytime you have two kind of opposite ends, you can say you have a pole.
That means that a molecule is going to have a positive end and a negative end. So that's the definition of polarity that you see right here. So it turns out there's two different types of polarity. The first one being
Bond polarity, and that's between two atoms in a bond.
Let's do a couple of molecules, or a couple of bonds, I should say. You have H
here,
and F.
Yeah, here we have two atoms, and
how do you know if it's polar?
Well, that's a really good question. That has to do with electronegativity differences.
So let's think of this as an electron. Remember, in electronegativity, that's the attraction of one atom for the electrons of another.
Well, let's pretend this is a pair. We both have one.
A pair of electrons, actually. So we got a pair of electrons, and we're fighting over it.
Yeah.
And right now, I'm stronger than Mr. Dimitrievich.
You have to really use your imagination on that one.
Not really. So if I'm stronger than him, the electrons live closer to me. So that gives me a negative. Actually, we say a partial negative charge and him positive charge.
So in this example right here, you're the fluorine,
I'm the
and I'm the
fluorine.
hydrogen.
Yes.
Fluorine is more electronegative than hydrogen is. And so in terms of this pair of electrons we're holding, we both are still sharing them because we both have ownership of it, but you have more ownership of it.
You might think of it this way. If we erase these two electrons, or the bond, it's as if the electrons live closer to the fluorine than the hydrogen, which gives the fluorine a partial, that's a funny little symbol, partial negative, and the hydrogen a partial positive charge. But it gets kind of mathematical on this, but like crazy easy math, right?
Yeah, so essentially, it doesn't matter if you really want electrons, right? You have a high electronegativity, and I also have a high electronegativity. It's all about electronegativity difference. So
the difference between one and the other, right? So there's tables, right? So you can see the table here underneath Mr. Dimitrievich. There's a table of the electronegativity values you can look up, right? And it turns out that fluorine, as you can see, is 4. So why don't you write 4 above the fluorine? And then the hydrogen, what's the number for that?
I believe it's
It's 2.1, right?
2.1 on that. We're doing this without having looked at the tables already. But
the point is, the difference between those two numbers is 4 minus 2.1, which is 1.9.
Yeah. Now, understand that whenever you have electronegative difference, we have these three variances: 0 to 0.4, 0.4 to 1.7, and 1.7 to 4.0.
So this is.
It's kind of in the range of a little bit more than just polar, but there is some flexibility with this.
So whenever you have a connection between an atom, you can determine if it's a polar bond, or actually, if you notice here, a non-polar bond, a polar bond, or an ionic bond. All right. Let's do an ionic one.
Well, an ionic one would be something like Na and Cl.
All right.
Now, in this case, we don't even draw the bond marker here because this is a full positive and this is a full negative. And if you take a look at the numbers between these two here, the gap is definitely more than 1.7.
Yeah. So we've got, what about one that we're like, let's do like oxygen to oxygen though.
Okay, so clearly in this case right here, if we have oxygen double bonded to another oxygen, I'm going to draw it the way it actually looks, even though I didn't put the electron pairs around there. Clearly in this case, they both have the same pole.
Yeah.
So if we were doing the sharing with this, it would have to be dead down the center. Neither of us can pull it closer to each other.
So what's the electronegative difference?
There'd be an electronegative difference of 0, which means that they're shared perfectly down the center.
So that means this is a non-polar bond.
So polar versus non-polar is kind of important. Now this is what we call bond polarity. Now what if we have an entire molecule?
So now we're switching to the concept of molecular polarity, the entire molecule. So when we talk about molecular polarity, it turns out to be polar, you have to have two things happen. Okay. Number one, the bond must be polar, which we just learned about, right? Which means the electronegativity difference has to be greater than 0.4 in the bond. Secondly, the shape, we learned about the shapes earlier, the shape must not cancel out, or another way to say it is the shape must be asymmetrical. That means not symmetrical. So let's do some examples. It's going to be real clear. So what's the first example you want?
Well, we did the very first example we did with Lewis structures was CO2.
Let's do CO2.
I'm going to draw CO2 out here, and we're going to draw it with all its glory. This is what it looks like.
All right, so we know that the shape here is linear triatomic. We learned that earlier in the chapter, so to speak. And is the bond polar? So let's just do our checkoff.
Yeah, well, we have two bonds here, right? And they're identical, so let's just take a look at one of them. So if you take a look at this right here, we have a carbon and an oxygen. If you take a look at the carbon and the oxygen on the table here, the polarity difference is greater than 0.4.
So that's a polar bond.
Right.
But the shape. Do you notice how the shape is symmetrical? And if the shape is symmetrical, it's going to be nonpolar.
Now, I'm doing something here that we probably should have talked about before. He did these delightful little partial negative and partial positive things. I'm drawing a dipole arrow, and if you see this dipole arrow, you notice how there's a little plus on this side, and it kind of shows the direction the electrons have shifted. So it's kind of a fast way, also super cool, to draw between two things. So we have this right here, where we have the electrons in this pulling in this direction, electrons in this pulling in this direction, and we look at the overall molecule, it's kind of like a tug of war, right? So if the carbon's in the middle and the oxygens are both pulling equally, is the carbon going in any direction?
No.
No.
So let me do another way to say this. If you think about this, this is the negative and this is the negative. I ask this simple question. Where's the center of the positive charge? On the carbon, right? Because he's the only positive guy. Where's the center, geometrically, of the negative charge? It's on the carbon, so they cancel each other out. Again, not polar.
All right, so let's do one with 3, because it's an example. It's not a very common example, but let's use this one right here. It's BH3. If you draw the structure, this is going to end up being a trigonal planar arrangement. This is what this
is
looks
a little bit weird in that there's actually no 8 electrons around the boron. That's not too worried about it. Now the question, of course, is the bond polar, B to H?
And this right here, this is a tricky one here, because the reality is that these are almost identical polarities.
So sort of kind of non-polar, but there's always some polarity between two atoms.
So I'm going to do this because I have the magic of a whiteboard. I'm going to change it to the most polar thing that we can have.
BF3.
Yeah, let's do F, F, and F.
So this one is polar bonds. B and F, big change, right? 4.0 for boron, for fluorine, and boron is much lower than that. So it's a polar bond, but again, we ask the simple question: where's the center of positive and negative charge? And of course, the way you've drawn this, all the positives are on the boron. And if you think about the central, right, because it's trigonal planar, it's going the center of the negative charge is going to be on the boron, so they cancel out. So it is a symmetrical shape, not asymmetrical. So
Yeah,
I've shown two nonpolars.
Yeah.
We need to flick to something that might be polar. Right?
Yeah, and by the way, let's use this structure as an example here. Even though we have 3 things pulling, they're pulling identically. But what if we just did this by the magic of my eraser? What if we just changed one of these to, let's say, a Cl?
Oh, yeah. Because, of course, the fluorines are going to pull more because they're stronger electronegative. The chlorine won't pull as much. So it's going to cause the center of negative charge to be kind of over here because the chlorine can't pull as tight.
And so what we sometimes do here is we draw an overall dipole. So we want to kind of point out where the overall negative charge is, or partial negative charge. So in this molecule, we'd be going up this direction because over here is where we'd have the more partial negative charge. So understand, just because 3 things are pulling out, if we have a tug of war and one of these pulls is greater, it's going to win.
So let's do one that has 4 attachments. What about carbon tetrafluoride, which is CF4?
So it's going to look something like this in the old school ways if we didn't understand that we have shapes. I'm not drawing electron pairs around the outside.
So, of course, when that shows 90 degrees. Of course, we actually know that it goes to 109 degrees when you think about 3-dimensional shapes, which he's now attempting to draw on a flat board, a 3-dimensional shape. So we've now got the carbon tetrafluoride. Between carbon and fluorine is the bond polar. Of course it is, because fluorine is crazy strong, carbon is medium, I guess.
Yeah, so in each case here, the electronegativity difference is going to cause the electrons to shift towards the fluorine.
But again, guess what we have? We have a shape that cancels out. The fluorine's the center of the negative charge, is on the carbon. Of course, the carbon is the positive, so it's going to cancel out.
And what's weird is it's hard to think 3-dimensionally. Like if we were to do this and we were to say, hey, we have something in the middle and 4 people are pulling exactly opposite, all of us will be able to see that these cancel each other out, right? But the same thing works 3-dimensionally. If even though it doesn't appear the way we've drawn it, if equal pulls are in all directions, and this is a symmetrical molecule, they're going to cancel each other out. Now, just like we did before, if we change even one of these, and by the way, I've gotten lazy with drawing the structures, but let's say I took that F, and let's say I made it I.
Yeah.
The arrows are still all going to stay the same, right? But the electronegativity difference between carbon and iodine is going to be less than carbon and fluorine. So in this structure here, if we were drawing the same thing, let's say we made this into I, by the magic of me being able to erase, I apologize for those who had already drawn this. Won't the pull this direction here for electronegativity be less than the pull in this direction?
So the electrons are going to be pulled off to the left as you've drawn it. Sort of left and up, I guess. So let's do one that has like 3 connections. Well, at least sort of, right? Now remember, we've done ammonia before, NH3, but when we draw it, it has kind of that extra lone pair of electrons, I like to say, on the top, so to speak. But that structure isn't exactly the way it's really shaped, though, right?
So remember, we always draw the template, and so when we draw the template out, it's going to look like this. And we always like to draw a little ghosty, a space where we keep the electron pair, just to remind us that that's occupying space.
So it has sort of that tetrahedral shape, but this is an extra pair of electrons. So now we have an interesting case. The NH bond is polar, but this molecule is asymmetrical, right?
So you can think of it as these three are all pushing up, and there's nothing pushing back down.
Right.
So therefore, the overall dipole moment would be this way. In other words, this side right here is going to be partially negative overall, and this side is going to be partially positive.
Another way I like to think about it is if you think about the positive charge is the hydrogens. These are all positive, partially positive. Where is the center of the positive charge? It's at the base of this pyramid. Remember, we're now talking about a trigonal, a triangular pyramid. At the base of the pyramid, that's where your positive charge is. And of course, the negative charge is on the more electric atom.
So we'd
of
be
nitrogen.
shifting up.
There's a difference in the charge there. Let's do one more example.
Let's try water, H2O, which again, we've done the Culture strategy a bunch of times. So I'm going to draw it the way it would look in a Lewis structure. And I want to point out something to you here, just for ease of this. If you ever draw a Lewis structure by itself, keep the two atoms that are the same next to each other. Because if you draw it like this, it's going to look as though these two things here are canceling each other out. Just a simple tip, the more you know. So this is the way it looks here structure-wise, and if we drew it in a three-dimensional structure, it's going to look very similar to this, because if we put our O in the middle, right, and we put our ghosty here and another ghosty down here on an angle, our hydrogens are going to kind of come off like this, right? Here and here. It's a bent shape.
So again, we have this simple question. Are the bonds polar? Yes. The difference between O and H is more than 0.4. And then we have see, this is a asymmetrical shape. It's not symmetrical. So again.
Yeah, right here, each of these bonds, the electrons are shifting towards the oxygen. So overall, they're moving in this direction. These electron pairs right now, they are not pushing back. So overall dipole moment, and I love how you do this here. So you talk
So
about
again, where's the negative charge? It's on the oxygen, because he's the more electronegative atom. The positive charges are on here, actually partially positive, but where's the center of the positive charge? Here. Notice the positive and the negative are not in the same place, so they cannot cancel out. That's why we say this shape doesn't cancel out.
So this is what we call a polar molecule, just based on the fact that it's not symmetrical.
And it's super important polar molecules matter. If water's not polar, living things don't live.
That's a pretty good thing to be thankful.
Yeah. So later on, we'll talk about polarity and its importance on the world. But
yeah, boiling point. I think the next video we're going to talk about intermolecular forces.
Yeah.
Stay tuned.
We'll see you in class.
Indeed.